So now let's look at the second method. That's the simplex method. Right, to see that this method is applied. This method is applied where there are two or more products under consideration. Where there are two or more products. Where there are two or more products under consideration. Where there are two or more products under consideration. So now let's look at the steps forward. Steps forward. Steps forward. Number one, formulation. Number one is formulation. Formulation. Number two, changing the inequalities to equalities. Changing the inequalities to equalities. Changing the inequalities to equalities. And introducing basis elements. And introducing basis element. And introducing the basis element. You'll see that changing inequalities to equalities and introducing the basis element. Number three, preparation of initial simplex table. Preparation of the initial simplex table. Preparation of the initial simplex table. Number four, testing the optimality for the first table. Testing the optimality of the initial table. Testing the optimality of the initial table. Number four, interaction with the subsequent tables. Interaction with the subsequent table. If the initial table was not optimal. 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 Number six, interaction with the optimal. Interaction with the optimal table. Interaction with the optimal table. Good. Those are the steps forward under simplex. NB. Number one. Optimality is met. Optimality is met when row DJ elements. Optimality is met when row DJ elements are all zeros or negative. Optimality is met when row DJ elements are all zeros or negative. NB number two. After developing the initial table, comma, from row DJ, pick the maximum amount, then use the selected pivot. Then use the selected pivot element. To get the ratio to get the ratio. Use the selected pivot element to get the ratio by dividing the values, by dividing the values by those elements, by dividing the values by those elements, full stop. Then pick the lowest ratio, then pick the lowest ratio, then pick the lowest ratio across the column, then pick the lowest ratio, then pick the lowest ratio across the column. Pick the lowest ratio across the column. Now let's look at derivatives. Derivatives. One is CJ. One is CJ. So that this contains the contribution margin. This contains the contribution margin. This contains the contribution margin. Number two, ZJ. 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 This shows the increase or decrease in profit. This shows the increase. This shows the increase or decrease in profit. This shows the increase or decrease in profit as a result of acquiring an extra unit. 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 Full stop. Then what to say that? For the first table, ZJ is equals to 0. For the first table, ZJ is equals to 0. And then number 3, we have DJ. Is that? This shows the net. This shows the net increase. This shows the net increase in profit. This shows the net increase in profit for acquiring an extra unit. 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 Then you can write this formula. So to get DJ, it's CJ minus ZJ. Good. So now I want us to do an illustration. Now there is a question we had done yesterday. Do you remember the question where we had product X and product Y? Can you go back to your notes? The one we did yesterday. The first illustration we did at a graphical method. Yeah, where the contribution margin for X was 3,000. It was 3,000 X plus 2,000 Y, of which you got 175 as the optimal profit. Optimal profit. And then the optimal production, XY. X was it 25 or 50? Which one was 25? Which one was 50? X 25, Y was? Yeah, was 50. Of which we also computed the slack for the resources, of which for the binding resources was 0. And then for labor was 125. We also computed for the shadow price. While the shadow price for non-binding is 0, This one we got, was it? Which one? This was 625, huh? The first one was? Yeah, 250. Now, if you had to have read the same question, but now we apply the simplex method, we obtain the same results. So open with me September 2021, question 2. September 2021, question 2. Do question 2B. Question 2B. Zakem Limited produces two products, namely Arcon and Xenon. So you have Arcon, then let it be X, then there is Xenon. Let it be Y. The product passed through 3 departments, namely assembly, finishing, and packaging. There is a maximum of 200 hours in each of the assembly and finishing departments. In addition, a maximum of 400 hours of packaging are available for packing Arcon and Xenon. The table below shows the number of hours required per unit of each product. So we have department, the assembly, finishing, and packaging. Then we have hours required per unit of product, Arcon and Xenon. Each unit of Arcon and Xenon gives a profit contribution of 3,000 and 2,000 units respectively. Required. Formulate a linear programming model to solve the above problem. So first of all, we formulate that. To formulate in formulation, we start with the objective function. Say that you maximize Z, that is 3,000 for X, then Xenon is 2,000 of Y, subject to, then you factor in the limiting factor. We start with this. We have assembly department. We have finishing. And then we have Xenon. Is 2 of X plus 3 of Y less or equal to 4 of X plus 2 of Y less or equal to 5 of X plus 3 of Y less or equal to. Now, the first paragraph I told that, the second sentence, there is a maximum of 200 hours in each of the assembly and finishing department. Assembly and finishing, we have a maximum of 200 hours, 200 hours. In addition, a maximum of 400 hours of packaging are available for packing. So it's packaging, sorry. And for packaging, we have a maximum of 400. Then you have to come up with a negativity that X, Y should always be greater or equal to 0. So that's how you formulate. Number 2 of the question. Using Simplex method, solve the linear programming model formulated in B1 above. So now using the Simplex. So let's go to step number, to the steps in simulation. I mean in Simplex. So that step number 1, you do what? You formulate, of which you have already formulated. Then step number 2. Step number 2, you change the inequalities to equalities. Now these are what we call the inequality, less or equal to. We change them to equality and then you introduce the basis element. Now, in this case, we have 3 limiting factor: assembly hours, finishing hours, packaging hours. They are 3 limiting factor. So if you have 3 limiting factor, you introduce 3 basis elements. So that means I say that you change the inequalities to equalities, and then you introduce the basis element. How do you do that? So you'll say maximize Z is 3,000 for each unit of X plus 2,000 for each unit of Y. Now, since we have 3 limiting factor, you introduce 3 basis elements: 0S1, 0S2, 0S3. So you have 3 bases: S1, S2, S3. Now, this 0, you see, like for example, this 3,000 was a contribution margin. Now, the basis element you introduce, you assume they have a profit of 0. That is 0 of S1, S2, S3. Then subject to, then you factor in this: 2x plus 3y plus S1 is equals to 200. Finishing now will be 4x. In short, this one is presenting basis 1, basis 2, basis 3. So it's the second one finishing would be 4x plus 2y plus S2. You change the inequality to equality. So it's also equal to 200. And then for packaging, it's 5x plus 3y plus S3 is equals to 400. Then x comma y should always be greater or equal to 0. Now, negativity does not change. The assumption still holds. So this was for finishing. This was, sorry, it's on for assembly. Assembly, finishing, and here we have packaging. Good. So that's the second step. Now, what was step number 3? Step number 3 was to do what? You develop the initial simplex table. It's also known as the first table. So initial simplex table, also known as the first table. How do we come up with this table? So here you have CJ, then we have the basis, product X, product Y, this is S1, S2, S3, then we have its value, and then we get the ratio. Now for the basis, we have 3 bases. We have introduced S1, S2, S3. Then we need CJ, we need ZJ, and we need row DJ. So how do we get that? This is how we develop the table. Now we say that CJ, now can you go back where you had derivatives? Look at the derivatives you have indicated. You see that CJ represent what? The contribution margin. Good. Now basis S1, S2, S3, the CJ are 0. The contribution margin is 0, 0, 0. We also have here the CJ. For X, it's 3,000. For Y is 2,000. S1, S2, S3, 0, 0, 0. I have 0, 0, 0. Then we fill in this. So it's 2, for example, the first one. S1, we say that it represents the assembly. So it's 2, 3, 2, 3, 4, 2, 5, 3. Then for the basis, you come up with what we call the identity matrix. You know what's the identity matrix? 1, 0, 0, 0, 1, 0, 0, 0, 1. What does it mean? This is what it means. For basis S1, here is S1. We had 3. I mean, we have 2x, 3y, and 1 S1. There is no S2, there is no S3. The second one, it's 4x plus 2y. This is S2. For S2, it's only one S2. There is no S1. There is no S2. Then the last one, 5x 3y, 5x 3y. Then we have 1s3. 1s3. So there is no S1. There is no S2. And then we have their values. For S1, which presented the assembly, we have a maximum of 200 hours. S2, we also have 200. And then packaging, we have 400. Next step, we get ZJ. Now, we have said that. Can you go back? What does ZJ represent? And then there is something we have said. For the first table, for the initial table, row ZJ element is always equal to 0. Okay, this is how we get ZJ. Now, to get ZJ, this is what you'll be doing. For example, for X, you'll take 2 times the contribution margin of 0. So 2 times 0, you get 0, plus 4 times 0, you get 0, plus 5 times 0, you get 0. So that's why all the element of the ZJ for the initial table is always equal to 0. We get DJ. How do we get DJ? Yeah, to get CJ, to get DJ, you take CJ minus ZJ. So to get DJ, you take CJ minus ZJ. 3 minus 0, you get 3,000. 2 minus 0, you get 2,000, 0, 0, 0. Now we test for optimality. Is our table optimal? And now let's go to NB. NB number 1, you see that? Optimality is met when row DJ element are all 0 negative. In this case, this is 0, 0, 0. These are positive. So therefore, they are not negative. They are not 0. So that means we have not yet met optimality. We have not yet met optimality. We have not met optimality. Let's go to NB number 2. No, just read NB number 2, what we indicated. Do you understand anything there? You don't understand, right? Now listen here. Now this is what it means. Now, if the table is not optimal, we need to come up with the second table. How do you develop the second table? From the row DJ, if it's not optimal, you select the maximum element. From DJ, give me the maximum element. 3,000. You take the maximum. Now, while you take the maximum, now that column forms the basis of determining the ratio. This element, the one we have here, will give us the ratio. And how do we get the ratio? Now, this is how we get the ratio. You'll take the values. For example, this one you have is 200, 200, 400. You take the value, you divide by the element from where you have the maximum before you get the pivot. Now, for example, the first one, you'll divide by 2. You take the value, you divide by 2. Where you have the maximum for S2 is 4, so you divide by 4. For S3, here the turning point we have is 5, so you divide by 5. That's how you get the ratio. So this is 100. This one you get an amount of 50. This one you get an amount of 80. That was that point I was trying to explain. Then from the ratio, you select the minimum value. Now, from the ratio, give me the minimum. 50. This is 50, you take the minimum. Good. Now, once you get the minimum, we want to determine what we call the pivot or the turning point. Now, the pivot is the meeting point between the maximum and the minimum. Here we have the maximum. Here we have the minimum. So where is the meeting point? The meeting point is where we have 4. Where we have the maximum, the element we have is x. Now, x becomes what we call the incoming variable. incoming variable, and is going to replace the basis which is minimum. Well, we have the minimum is coming from basic S2. So S2 becomes what we call the outgoing variable. I repeat again. While we have the maximum, that element becomes the incoming variable. It's going to replace one of the bases. Okay, this is what I mean by basis. Basis will help us to determine the basis of non-binding and binding resources. The one that will disappear, they are known as binding. The one that will refuse to disappear, they are called non-binding. So when we have the maximum, we take the element which is X. So X will replace one of the basis element. So that one is one of the binding. Then it's going to replace where we have the minimum element. And the minimum element is coming from S2. So S2 will be replaced by X. So from there, we can come up with a second table. So how do we develop the second table? Since the first table was not open, so come up with a second table. So you have Cj, then we have the basis X, Y, S1, S2, S3. We have the value, then we get the ratio. Then for the basis, we have S1, S2 is gone. Now who is replacing S2? Who's replacing S2? We have is X. Then here we have S3. Cj, Zj, Dj. So then we have the Cj is here. See that Cj represents the contribution margin. S1, the contribution margin is 0. S3 is 0. What about X? How much is the contribution margin of X? So the contribution margin of X we have is 3,000. Then we have the Cj here. Now the Cj here does not change, always be constant. For X is 3,000, Y was 2,000, S1 is 0, 0, 0, 0. Then, now here you need to pay maximum attention. Well, we have the pivot. Now we have the pivot from the basis element, which is S2. Now, this row now will form our new row element in the second table. And how do we get that? I'm saying that the X, you see now the basis one is remain, S2 remains, but X is a new variable here. So it becomes the new row element. So how do we get the new row element? From where we have the pivot, you take all the element in that row, you divide them by pivot. This is what I mean. You'll take 4 divided by 4, 2 divided by 4, 0 divided by 4, 1 divided by 4, 0 divided by 4, as well as 200 divided by 4. So that's how you get the new row element. So you'll take 4 divided by 4, you'll get 1. 2 divided by 4, you get 0.5. 0 divided by 5, you get 0. 1 divided by 4, you get a quarter, which is 0.25. 0 divided by 4, you get 0. And then 200 divided by 4, you get 50. Now that's what we call the new row element. What about for S1 and S2? Now to get S1 and S2, we have a formula. This is how we get them. You'll take original row element minus new row element times the balancing figure. You're saying that ORA is the original row element. NRA is our new row element. So we need to get for S1 and S2. So how do we get for S1? How do we get for S2? We start with the S1. Saying that you take original row element. Now for S1, these were the original row element from the first table. we had 2, 3, 1, 0, 0, and 200 up to this point. Then you minus new row element. So our new element we have in the second table is 4x. So we have 1, 0 0.50, 0 0.250, and we have 50. Then you multiply by the balancing figure. So how do we get the balancing figure? Now, from where we have the pivot, for S1, the balancing figure will be 2. For S3, the balancing figure will be 5. Assuming this is why we had the pivot, assuming this was the pivot, the turning point between the maximum and the minimum. Now for S1, now the balancing figure could be 3. This one also could be 3. So in this case, we are saying that you multiply by the balancing figure. For S1, where we have the pivot is 2. And that's how we get that. So 2 minus 2 is 0. 3 minus 1 you get is 2. That's 1. This one you get is negative 0. Is that 0.5? This one is 0. 200 minus 100 you get 100. Let's do the same for S2. We do the same. You take original row element, so not S2 but S3. For S3, you take the original row element. Now the original row element was from the first table. We had 5, 3, 0, 0, 1, and then we had 400. Then we minus the new row element. So we have the new row element here, which is 1, 0 0.5, we have 0, 0 0.250, and 50. Then you multiply by the balancing figure. So the balancing figure, from where we had the pivot, for S3, the balancing figure we have is 5. So we have 5, 5, 5, 5, 5. And what do you get? Well, you get 0. 3 minus 2.5, you get 0 0.5. This is 0. Here you get negative. Get 1.25. And then here we have is 1. 50 minus 5, you get 250. Get 150. Good. So we have all the new elements. Now for S1, this is 0. This is 2. This is 1. Negative 0.5. You have 0. You have 100. Here we have is 0. We have 0.5. We have 0. Negative 1.25. We have 1. We have 150. Now let's get ZJ. We get ZJ. So to get ZJ, this we see that this is what we do. At least we see that for the first table, all the element is equals to 0. So from the second table, this is what you do. For X, you will take 0 times the CJ. 0 times 0, you get 0. Plus 1 times 3,000 is 3,000. Plus 0 times 0. What do you get? You get 3,000. 2 times 0 is 0. 0.5 times 3,000 is 1,500. 0.5 times 0 is 0. So you get 1,500. 1 times 0 is 0. 0, 3,000 is 0. 0 times 0 is 0. So you get 0. Negative 0.5 times 0 is 0. 0.25 times 3,000, that's 750. Negative 1.25 times 0, that's 0. So you get 750. Then you have 0, 0, 0, 0, 1 and 0, that one is still 0. So you get 0. Then for the value, you take 100 times 0 plus 50 times 3,000. You get 150, right? 150 times 0 is 0. So that is how much? 150. Good. Then from there, now we get DJ. See that to get DJ, you take Cj minus Zj. So it's Cj 3000 minus 3000, you get 0. 2 minus 15 you have is 500, 0, negative 750, 0, negative 150. We test for optimality. Optimality is met when row dj elements are all 0 or negative. Is this the case? It's not the case. In this case, we have a positive value here, which is 500. So that means we have not met the optimality. So if it's not optimal, you select the maximum value of the row dj. The way you did here, you took the maximum. So the maximum value we have is 500. So take the maximum. Then where you have the maximum, that column, now y will become the incoming variable. Incoming variable, and it's going to replace one of the basis element, either S1 or S3. So the one that will be replaced is what we call now a basic element. I mean binding element. And which one will go? To determine which one will go, you have to compute the ratio. And how do you compute the ratio? So that to get the ratio, you take the values. This is 100, this is 50, this is 150. You divide by, from the element where you have the maximum, that column. So for S, this one you divide by 2. For this one, you divide by 0.5. From this one, you divide also by 0.5. And that's how you get the ratio. Here you get 50, 100, you'll get an amount of 300. Then from the ratio, you pick the minimum. And the minimum we have is? So we have the minimum. Then from where we have the minimum is from S2, I mean S1. Now S1 becomes the outgoing variable. So that means Y now will come to replace S1. So where you have the maximum becomes the incoming variable, where you have the minimum becomes the outgoing variable. And we need to get the pivot. How do we get the pivot? Pivot is the meeting point between the maximum and the minimum, which is meeting point here we have is 2. Good. So from there now we go, we proceed. We have not met our parity. So now we go to the third table. How do we develop the third table? Cj, we have the basis x, y, s1, s2, s3. We have the value. Now for the basis, S1 has been replaced by Y. Here we have X. Here we have S3, CJ, ZJ, DJ. So we start with the CJs here. Y, CJ represent the contribution margin. The contribution margin for Y was 2,000. X was 3,000. Here they are. X is 3,000, Y is 2,000. S3, that is 0. Then we need to get this other CJ. That one does not change. It means to be constant. X, we have is 3,000. Y, 2,000. S1 is 0. S2, 0, 0, including the value. Then the next element, we have our new member here. Our new member is Y. Because S has gone, S1 has gone, has been replaced by Y. So that means Y will form the new row element. And how do you get the new row element? To get the new row element, which was from S1, which has been replaced, you will take all the elements of that row, you divide by the pivot. Like for example, this one will be 0 divided by 2, 2 divided by 2, 1 divided by 2, negative 0.5 divided by 2, 0 divided by 2, and 100 divided by 2. That's how you get the new row element. So take all the elements of S1, which have been replaced by 1, you divide by the pivot. So 0 divided by 2, you get 0. 2 divided by 2, you get 1. 1 divided by 2, you get 0.5. Negative 0.5 divided by 2 get negative 0.25. 0 divided by 2 get 0. 100 divided by 2 you get 50. Now you have what you call the new row element. What about x? What about S3? So to get x and to get S3, we use the formula. Original row element minus new row element times the balancing figure. We start with x. Now x, you take the original row element. Now that's from the second table. X, the original row element we had was 1. We had 0 0.5, 0, 0.25, 0, and we had 50. Then you minus the new row element. Y becomes our new row elements, which we have 0, 1, 0.5, negative 0.25, 0, and 50. Then you multiply by the balancing figure. So to get the balancing figure for x and S3, we go where we have the pivot. But we have the pivot from that now column. For x, the balancing figure is 0.5. For S3, the balancing figure will also be 0.5. So we have 0.5. What do you get? So you get is 0.5. So when you get 0, then you get negative 0.25. And what about that? That's 0. That is 25. Complete for me that one. You're getting negative? Minus, minus. That one becomes, what's the 0.25? You get? 0 point? Then you do the same for S3. For S3, you take the original row element. For S3, this was the original row element. We have 0, 0 0.5, 0, negative 1.25, 1, and 150. Then you minus the new row element. These are our new row element. You have 0, 1, 0 0.5, negative 0.25, 0, and 50. Then you multiply by the balancing figure. Now for S3, how much is the balancing figure? So you have it's 0.5. So what do you get? So this one you get 0. So one you also get 0. So when you get negative 0.25. When you get 1. So when you get 125. How much is this? Sorry? Sorry? The first one for x. This one is 1, eh? Sorry? The first one for x? Which one? This one. This one. This one. You are getting 0.375. 0.375. Negative 1.375. So that means for x, we have is 1, we have 0, negative 0.25, 0.375, 0, and we have 25. Now we have is 0, 0, negative 0.25, negative 1.375. We have 1, then we have 125. Now we can get ZJ. So to get ZJ, we take 0 times 2,000, which is 0, plus 1 times 3,000, plus 0 times 0, you will get 3,000. 1 times 2,000 is 2,000. 3,000 times 0 is 0. 0 times 0 is 0. So we get 2,000. 0.5 times 2,000 is 1,000. Negative 2.5 times 3,000 is 750. 1,000 minus 750, that's 250. Negative 0.25 times 2,000, you get negative 500. 0.375 times 3,000, what do you get? You're going to get 1,250 minus 600, you get 650. Then 0, 0, 0. 50 times 2,000, that's 100. 25 times 3 is 75. So you'll get an amount of 175. Yes? It's negative? 1.125. 1.125. Which one? So this one was 0.375. Which one? This one? This one? Is how much? Negative 1.125. Negative 1.125. So still this one will be 0. So that one does not affect 650. Now we get DJ. So DJ is CJ minus ZJ. 3 minus 3 is 0. 2 minus 2 is 0. 0 minus 250 is negative 250. Negative 650. We have 0. Negative 175. Have we attained our optimality? So now once we achieve our optimality, now I think we have the optimal solution. And how do we determine how many we need to come up with? So let me come up with a summary. Product X, Y. Product X was Alcon, and then we have the value. Then we have the resources. Our resources for the limiting factor, there were 3. We had assembly. Then we had finishing. And then we have packaging. Then we have their status. We need to get the stack. We need to get the shadow price. Now let's go back to some terminologies that you defined yesterday. Terminologies. Under the last terminology, there was an NB I told you to indicate. NB. The first one was what? Value. And you see that, what does value mean? This means units produced. So value will represent the number of units produced for X and for Y. How do you determine that? Now, from the optimal table, these are the values. For Y, it's 50. So Y will produce 50. Then for X, the value is 25. Then we have the resources: assembly, finishing, and packaging. And here they are. Assembly was S1, finishing was S2, packaging was S3. Now from the optimal table, S1 was replaced by Y, S2 was replaced by X. Now the one that were replaced, that's what we call binding resources. So assembly and finishing, that's S1 and S2, they were replaced by Y and X. So both of them, they are binding. Also, this one is binding. Packaging refused to move. So that one becomes a non-binding. Non-binding. Then we get the slack. We see that slack is unused quantity at optimality. And for binding resources, always equal to 0. For non-binding, which was S3, S3 refused to move. And there was unused quantity, an amount of 125. Then we get the shadow price. How do we get the shadow price? To get the shadow price, you look at ZJ. See that ZJ shows the net increase or reduction. We produce an extra unit. S1 is 250. So I think that to get the shadow price, we'll take our ZJ. S2, ZJ we have is 650. S3, we have is 0. Remember, you see that for non-binding, shadow price is always equal to 0. Also, we have the optimal profit. Optimal profit. And this was the optimal profit, which is 175, which is the same as doing this. X, we have produced 25 unit, Y 50 unit. For each unit of X, the contribution is 3,000. For each unit of Y is 2,000. So we take 3,000 times X, which is 25. Then you add 2,000 times each unit of Y, which is 50. We'll get 175. Good. And this is a question we have done using the graphical method. So you can copy now. Open May 2018, question 4C. Yeah, that should be 625. The firm manufactures two products, X and Y, subject to constraints on three raw materials, raw material 1, raw material 2, and raw material 3. The objective of the firm is to select the product mix that will maximize weekly profit. So that means the objective is to maximize. Each unit of product X earns a profit of 2 shillings, whereas each unit of product Y earns a profit of 1 shilling. So that means formulation is maximize Z. Each unit of X earns a 2 shillings profit. So it's 2 of X and 1 shillings for each unit of Y. 1 Y. Then subject to details of the raw material required for the production of product X and Y are given below. So you have raw material 1, 2, and 3. We have the maximum quantity. Then you have the quantity required per unit of production. So subject to raw material 1, raw material 2, raw material 3, then we have non-negativity. For raw material 1, for product X, we require 3, product Y 0. So that means it's only 3 of X less or equal to, the maximum quantity we have is 27. Raw material 2, it's 0 of X, 2Y. So it's 2Y less or equal to, for raw material 2, we have that units. And then raw material 3, it's 1 of X, 1Y. So it's X plus Y less or equal. So the maximum quantity we have is 20. Now negativity is X, comma Y should always be greater or equal to 0. Required. A linear programming model for the firm. So we are done. Part 2. The optimal product mix using the Simplex method. So we have to use the Simplex method. Now under Simplex, the first step, after formulation, you change the inequalities to equalities, and then you introduce the basis element. So here you have 3 limiting factor. This one will be S1, basis 2, basis 3. So it will be maximize z is 2 of x plus 1y plus OS1, 0S2, 0S3, subject to raw material 1, it's 3x plus S1, that's raw material 1. So this one is equal to 27. 2y plus S2 is equals to 30. That's for raw material 2. And then x plus y plus S3 is equals to 20. And that's the raw material 3. X comma y should always be greater or equal to 0. That's non-negativity. Then the next step, you come up with the first or initial table. Initial simplex table or the first table. So we have CJ, have the basis X, Y, S1, S2, S3, the value and the ratio. Then for the basis, we have S1, S2, S3. Then we need to have CJ, ZJ, and DJ. CJ for the basis, it's 0, 0, 0. XY. So here we only have 3x. There is no y. Then there is 1s. 2y. So for S2, that's raw material 2, is 2 of y. So that means there is no x. Then 2y. 1x, 1y, 1, 1. S1, S2, S3, we use the identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. Then we have the CJs. Each unit of X, the contribution margin is 2 shillings. Y is 1 shilling. 0, 0, 0. We need ZJ. See that ZJ for the first table is always equal to 0. And we have the value. S1, which is raw material 1, S1, we have a maximum of 27. We have a maximum of 30. Here we have 20. We get DJ. So to get DJ is CJ minus ZJ. So 2 minus 0, you get 2. 1 minus 0 is 1. 0, 0, 0. Then you test for optimality. Optimality is met when row DJ elements are all equal to 0 or they are negative. In this case, we have 2 positives. So that means you have not yet met optimality. If optimality is not met, you take the maximum element in DJ, of which the maximum we have is 2. Now, once you get the maximum, from the column it's coming from, is coming from X. So that means X becomes an incoming variable and is going to replace one of these bases. So how do you determine which bases to be replaced? You compute the ratio. And how do you get the ratio? To get the ratio, you take the values, 27, 30, and 20. You divide by the element of the maximum. From where we have the maximum, that column. For S1, you divide by 3. For S2, you divide by 0. For S3, you divide by 1. So here you'll have it's 9, 0, you'll have 20. Then from the ratio, you take what? You take the minimum. In this case, the minimum is 0. Now let me explain something here. Now, if you take 0, which is very okay, if you take 0, everything will be 0 there. So 0 does not change the matrix. This is what it means. If you take 0, the same process will happen and it will develop the second table. But now the second table will be the same as the first table. So if you get a 0, that means you see all the elements from this case, it will be 0, 0, 0, 0, 0, 0. So that means the first table and the second table will be the same. So instead of replicating that, whenever you get a 0, you ignore the 0. You take the next one. Because if you take the 0, the second table will automatically be the same as the first table. So in short, you will prepare many tables to the same result. So you ignore that. So instead of 0 now, you take the next minimum, which is 9. I hope why I've explained why. If you take 0, still is okay. But now you'll develop the second table, which will be the same as a replica of the first table. So there is no need to prepare 2 tables which are the same. So take the next one, which is the minimum. And that's 9. Now from where the minimum is coming from basis S1. So S1 now, it will go, becomes the outgoing variable and will be replaced by X. And then we need to get the pivot. Pivot is the meeting point between the minimum and the maximum, of which it's 3. So from there, can develop the second table. I'll develop the second table. So Cj basis X, Y, S1, S2, S3, value and ratio. And then for the basis, now S1 is gone, has been replaced by X. Then we have S2, S3. Then we have Cj, Zj, Dj. Now we get the Cj, X, each unit of X, the contribution margin was 2. S2, S3 is 0, 0. Cj here, we see that Cj does not change. Each unit of X is 2, Y is 1, 2, this is 1, or 2, this is 1, 0, 0, 0. So 0, 0, 0, including the value. Then we need to get the new row element. How to get the new row element? Our new member here we have is X. And X is coming from S1. So you take that row element, you divide all the element by the pivot. You'll take 3 divided by 3, you get 1. 0 divided by 3, you get 0. 1 divided by 3, you get that 0.33. 0 divided by 3 is 0, 0. 27 divided by 3, get 9. So now we have the new row element. So how do we get for S2 and S3? To get S2 and S3, you take the original row element minus new row element times the balancing figure. Compute for S2, S3. Original row element for S2. Take this original element. You had 0, 2, 0, 1, 0. Then we have 300. 300 by that. Then you minus new row element. This is our new row element. We have 1, 0, 0 0.33, 0, 0, and 9. Then you multiply by the balancing figure. So where you have the pivot, now that column will give us the balancing figure. For S2 is 0, for S3 will be 1. So here you have is 0. Do the same for S3. You take the original row element. You have 1, 0, 0, 1, 0. And then we have 20. Then you minus the new row element. The new row element is for X. We have it's 1, 0, 0 0.33009. Then you multiply by the balancing figure. Now for S3, the balancing figure we have is 1. So that's 0. That's 0. Negative 0.33. That's 1. That's 0. Here we have is 11. So S2 have is 0, 2, 0, 1, 0, 30. So you can see in this case, it has remained to be the same. Nothing has changed. Yeah, so that means if you could have taken this 0, all the other elements could remain to be the same. S3, we have it 0, 0, negative 0 0.33, 1, 0, and we have 11. Then we get Zj. To get Zj, it's 1 times 2, you get 2, plus 0 times 0 is 0, 0 times 0 is 0. So you get 2. 0 times 2 is 0, 2 times 0 is 0, 0 times 0 is 0. 0.33 times 2, you get 0.66. That's 0, that's 0. 0.66. 0, 0, 0. 0, 0, 0. 2 times 9 is 18. 0, 0. Get 18. We get dj. So to get dj, you take cj minus zj. 2 minus 2, get 0. 1, negative 0.6600, and negative 18. Have we made the optimality? Optimality is not met. We have a positive value here. So that means we have not met the optimality. So from where we have, if you have not met the optimality, you take the maximum value from the row dj. And this is the maximum. Now where it's coming from, it's coming from y. So now y becomes our new incoming variable, yes? That mistake where? Sorry? Which one? This one? The original one? This one? It was 1, 1. Oh, this was 1, eh? Then all zeros, this was 1, eh? So this one will be 1, eh? That's okay. This one will be 0. This one will be 1, eh? Yeah. So that means, yeah. S3, so 0, that's 1. Also, this one will change. So this is 1, and this is 0, and this is 1. So after all, it won't change, eh? It won't change anything, because if you take those elements, you multiply by 0, it remains to be 0. So now y becomes the incoming variable. So y is going to replace either S2 or S3. So which one will go? To determine which one will go, you compute the ratio. And to get the ratio, you see that you take the values, 9, 30, and 11. You divide by the pivot. I mean, you divide by where you have the maximum element, that column. So this one you divide by 0. This one you divide by 2. This one you divide by 1. This is 0. This is 15. This is 11. Then from the ratio, you take the minimum. The minimum is good. In that case, we ignore 0. Are you together? So you'll take? Okay, 11. So that means where we're getting the minimum, that's S3. So S3 becomes the outgoing variable. So that means y will place S3. So that means X, which was S1, and S3, both of them, they are what you call the binding resources. If they are binding resources, slack is 0. S2 is non-binding. So now we can be able to get the pivot. So the pivot is the meeting point between the minimum and the maximum, which is 1. So now we can develop that table. Cj, we have the basis, we have X, Y, S1, S2, S3, and then we have the value. So here we have X, S2. Now S3 is gone, will be replaced by Y. Cj, Zj, Dj. Cj for X, each unit of X, the contribution margin is 2. Each of Y is 1. S is 0. Here, x is 2, y is 1, 0, 0, 0, including the value. Now we need to get the new row element. How do you get the new row element? You take the pivot, the meeting point between the maximum and the minimum. Now the pivot is on the third column. So you change all those members of the column by dividing them by the pivot. So it will be 0 divided by 1, you get 0. 1 divided by 1, you get 1. Negative 1.33 divided by 1, you get negative 1.33, sorry, 0. That one is 0. 1 divided by 1 is 1. 11 divided by 1 is 11. So now we have our new row element. What about x and s2? To get x and s2, use the formula original row element minus new row element times the balancing figure. So we need for x and s2. So for s2, I mean x here, the original row element, you take it from the second table, add 1, 0, 0.33, 0, 0, 9. Then you minus new row element. So these are our new row element. We have 0, 1, negative 0.33, 0, 1, and 11. Then you multiply by the balancing figure. Now the balancing figure from where you have the pivot. That's why you get the balancing figure. For x is 0, for s2 we have is 2. So 0, 0, 0, 0, 0, 0. Get 1, 0, 0.33. We have 0, 0, 9. For S3, the original row element. This is S2, I mean S2. The original row element we had was 0, 2, 0, 1, 0, and that. Then you minus the new row element. So for y is our new row element. We have 0, 1, negative 0.33, 0, 1, and 11. Then you multiply by the balancing figure. For S2, the balancing figure here we have is 2. So that's 0. That's 0. This is positive 0.66. That's 1. That's negative 2. And that's 8. Good. So here we'll have for x, we have it 1, 0, negative 0.33, 0, 0, 9, 0, 0, 0.66, 1, negative 2, and we have 8. Now we get ZJ. 1 times 2 is 2, 0, 0 is 0, 0, 1 is 0. So you get 2. 0 times 2 is 0, 0 times 0 is 0, 1 times 1 is 1. 0.33 times 2 gets 0.66. Negative 0.33 times 1, get negative 0.33. 0.66 minus 0.33, you get 0.33. 0 times 2 is 0, 1 times 0 is 0, 0 times 1 is 0. 0 times 2 is 0, negative 2 times 0 is 0, 1 times 1 is 1. And then to get the value, now the value represents now our optimal profit. So it's 2 times 9, you get 18. 0 times 8, that is 0. 1 times 11, you get 11. 11 plus 18, you get 20, 29. Then you can get DJ. So DJ, it's CJ minus ZJ. 2 minus 2 gets 0. 1 minus 1 is 0. Negative 0.33. 0. Negative 1. Negative 29. All the row DJ elements are 0 and negative, so we have made the optimality. So how many units will we produce? So we have the products, X, Y, then we have the value. We see that value represents the number of units produced. So you get the value from the optimal. X will produce 9 units. Y will produce 11. Then we have resources. For resources, we had raw material 1, raw material 2, raw material 3. Determine their status. We can also get the slack, though was not part of the question, as well as the shadow price. Now, raw material 1 was S1, S2, S3. From the optimal table, S1 is gone, S3 is gone. So the one which are gone, they are called binding resources. So that one is a binding. This one is also binding. Raw material 2 has refused to go. That one is non-binding. We get the slack. Slack for the binding resources is always equal to 0. For non-binding, which is raw material 2, which was S2, we have 8. Then we get the shadow price. So to get the shadow price, you look at the ZJ. So for S1, we have it 0.33. For S2 is 0. I will see that for non-binding, shadow price is always equal to 0. And then for S3, we have is 1. What about the optimal profit? Now, optimal profit we have is 29, which is the same as doing this. The profit function is 2 of X, 1 of Y. So it's 2 of X, of which X we have produced 9, 1 of Y. 1 shillings for each unit of Y, which is 11. If you do that, you will get 29. It was the same as that. Good. And you're done with that. So now you can copy. So you're done with now linear programming. So now you're remaining with one topic, that's descriptive statistics. And that one, I won't teach it. So I taught last semester. So I'll share with you the link. I've already uploaded it to our YouTube. So I'll share it. So you go through it. Also, I'll share the notes. Yeah, because it's the same content. So I'll share, kindly make sure you watch that video. And then I'll also share the notes on that. So that now we start our revision.